Hey everyone, I'm Neil, and welcome to CS170's first week of video content. This is the first video in our mini lecture series, and this video was actually created by our former TAs, Avi and Charles. So the mini lecture videos are meant to provide you with kind of like an intuition as well as an overview of each week's core algorithms. They're meant to help you show how we build from scratch, kind of how we construct these pretty complex and advanced algorithms. So later this week, we'll also have some discussion walkthrough videos as well as some homework walkthrough videos. And later this semester, we'll have some exam prep as well as like miscellaneous videos coming out too. So if you ever have any questions regarding, what type of video content we're putting out or like the schedule of our videos, please feel free to check out the production company's Piazza post and feel free to leave like a follow-up comment or whatever. So yeah, good luck and hope you enjoy these videos.
All right, let's go ahead and dive right into our mini lecture. So the first topic for today is going to be big O notation. And this should be a concept that you covered in 61A, 61B, and this will be a very quick overview of what big O is. So the general definition of big O is a measure of how well a computer algorithm scales as the amount of data involved increases. And so most commonly, you'll see a function f of n is equal to O of g of n, big O. And this big O, all it's stating is that my function f, the runtime of my function f is capped or limited by big O of g of n, so the runtime of g of n. And so asymptotically, all we're saying here is that f is growing at most as much as g. So the example in the textbook that they give is, let's say f of n is equal to 2x plus 20, and g of n is equal to x squared. In this case, if I want to figure out what is, the big O, or is f of n big O of g of n, how would I figure this out? My goal is to figure out, is the rate of f of n capped by g of n? And so the strategy here is to take the limit of f of n over g of n. You would say the limit of f of n over g of n as n goes to infinity is equal to what? So in this case, it's a limit of n goes to infinity of 2n plus 20 over n squared. And in this case, you can see that n squared is far greater than n. One is linear, one is polynomial. And so in this case, you would go ahead and say this goes to 0. And this means that my n squared term, as n gets bigger and bigger, supersedes or is superior compared to my 2n plus 20 term. So by doing this kind of strategy of taking the limit of f of n over g of n, we can come up with three key cases. We have big O, we have theta, and we have omega. So big O is stating that asymptotically, f grows at most as much as g. So in the case of where you're trying to say that, okay, my upper bound of the function, the upper limit of the runtime of a function, you use big O. When you want to set the lower limit, and here the lower limit is you're essentially just flipping the two. You're saying that if g of n is equal to big O of f of n, then you could state that f of n is equal to omega of g of n, where in this case you're saying that f grows at least as much as g, so the lower bound and the upper bound. And then last but not least, you have theta. And here when I say f of n is equal to theta g of n, I'm essentially just saying that if the upper bound and lower bound both match, then asymptotically they're growing at the same rate. So in order to prove these rules, there are three key limit rules. You take the limit as n approaches infinity of f of n over g of n, and you run this for the three cases. So if I have over here limit as n approaches infinity of f of n over g of n, there are three cases in which I can prove either big O, theta, or omega. So in this case, the one we did above, where we had f of n over g of n for 2x plus 20 and x squared, we saw that this was 0. And we can easily see that why big O makes sense is because our g of n term kind of is superior to f of n, it's far greater, and this limit, once it goes to 0, proves that f of n is equal to big O of g of n. Similarly, if I went ahead and did omega first, I would see over here that if I take the limit as n approaches infinity of f of n over g of n, and this went to infinity, what does this mean? Well, this is essentially saying that f of n is far superior or far greater compared to g of n. So as my input n scales, the kind of runtime of f of n is at minimum g of n, but f of n obviously is much larger. So this would imply that f of n is equal to omega g of n. And then last but not least, if both of these hold true for a function and your limit n approaches infinity, f of n over g of n is equal to some constant, then you can very easily say that, okay, they both have the same growth rate, and thus f of n is equal to theta of g of n. And so asymptotically, they have the same growth rate. That is Big O in a nutshell. I will see you in the next section. All right, so in this video, we'll be continuing our mini lecture, learning about recurrence relations and a recap of master theorem, and then the proof of why master theorem works. So if you remember from lecture, the whole core gist of a recurrence relation or master theorem stems from the fact that you have a divide and conquer algorithm that follows a generic pattern. So we'd say that we start off with a problem of size n. So over here we'd say a problem of size n that at every single level or every single step of recursion, you're recursively solving by a subproblems, and each one of these a subproblems has a size of n over b. And so you're essentially starting off at one single point. For example, this would be our size n node. And at every single level of recursion, you're breaking this down into a subproblems. So the branching factor here is a. And once you've broken this down into a subproblems at every level, each one of these has a size n over b, and so on and so forth. So you take one of these nodes and like the next level, break it down into a branching factor, in our case is 4, have 4 new nodes, and the branching factor here would be the branching factor is a, the size here would be n over b squared, so on and so forth. And so this was the gist of kind of the divide and conquer algorithm, and we saw by looking at this that this gave us a recurrence relation where we could go ahead and state that t of n is equal to, again, you have a subproblems, right? So branching factor of a times t of, and what is our new size now? Our new size is n over b. So at every single, stage of branching or every stage of recursion, you can kind of round this up as to say that we're now dealing with n over b size problem. And then we're going to go ahead and state that the work done at every level of this type of problem is equal to O of n to the d. And so d is again defined based on the problem that you're working with. This could be a value ranging from 0 to as big as you want. In the case of merge sort, for example, when you have sorted your two kind of subsections of arrays and you're combining them up into the final stage, that runs in O of n time. So d here would be 1. And that's a very quick example of how you'd solve, a very simple recurrence relation. So this again was the recurrence relation of a divide and conquer algorithm. And then master theorems went ahead and stated that if you have it in this form for, again, constants a, b, and d, then you can go ahead and come up with the following statement. You can say that t of n is equal to, and then there's 3 cases for master theorem. You could say that t of n, the runtime of this algorithm, is O of n to the d if d is greater than log b of a. You would say that the runtime of this algorithm is O of n to the d times log of n if d is equal to log b of a. And then last but not least, O of n to the log b of a. The runtime of the algorithm would be O of n to the log b of a if d is less than log b of a. So again, this is master theorem in a nutshell, and we saw these 3 cases. So what is the intuition behind 1, 2, and 3, and how is this being derived? That is going to be the next step. All right, so let's go ahead and prove why master theorem gives us these 3 notations. And in order to do so, I'm going to go ahead and define the height or depth and width of kind of this branching factor graph that we have drawn over here. So I'm going to copy this over, and I'm going to go ahead and just add some more details into this graph. So over here, we can very easily see that as this graph continues to expand, you'll have, again, branching factor 4 over here, and this continues on, ... You would eventually get to a size of 1, where you would stop and you have these individual nodes. And so the question becomes, what is the depth of this graph? And so the depth here is simply equal to, again, you're dividing by b at every stage, so you would get to 1 from n by log b of n, sort of steps or iterations. And so that's our depth. And then we also note that at every level, we are branching by a factor of a. And so based on that branching factor of a, we can very easily state that at level k, we would have a to the k nodes. And so if we are at level, or this like size 1 level would be level log b of n, we can very simply state that at the very bottom, the width of this graph, so width would be equal to a to the log b of n. Now, we know from logarithm formulas, and again, this is back to like 8th grade or 9th grade algebra, but we know that log a of x is equal to log c of x over log c of a. Again, just change of base with logarithms. This is a formula that we know. And so what we can do is we can simplify this log a to the log b of n and state that this is actually equal to a, and then we can go ahead and kind of use this neat trick here and say a log a of n times log b of a. And so this would be equal to n to the log b of a. So now that we've defined our width and our height, now the next step is to go ahead and prove how we're actually getting these three relations. So down below, let's go ahead and do just that. First thing first, we can go ahead and, we essentially need to figure out how much total work is being done at every level. So we notice that kind of at every single level, we are having a subproblem of size n over b. And we know for a fact that there are a to the k nodes at every level. So at level k, we're dealing with the fact that there are a to the k nodes. And for each one of these nodes, we stated above that at every level, we're doing O of n to the d work. That was this type of phrasing over here. And so if at every single node we have n over b to the 2 squared or n over b cubed, etc., we know that at level k, we're dealing with a node of size n over b to the k. And so we can say over here that at level k, we're doing a to the k. So we have a to the k nodes, and each one of those nodes is doing O of n over b to the k to the d work. Okay? And so hopefully that's very clear as to how we're getting that, because we said earlier that at every level that O of n to the d work is being done. And so if our n goes from n to n over b to the k level k, we're doing O of n over b to the k to the d work. And so we can simplify this phrase over here because our big O is only dependent on n to the d, and state that this is equal to O of n to the d times our a to the k times over b to the k to the d. And so I'm going to simplify this overall and state that this is a over b to the d to the k. So this is our overall work being done at every level. And so we start off at level 0. So we start off at level 0 and go and work our way down to log b of n leaps. And so we'll very quickly notice that this forms a geometric sequence. At level 0, we're doing O of n to the d work. And at level log b to the n, we're doing a lot more work. And again, this is all dependent on the ratio of a over b to the d. For example, we can come up with 3 cases that will help define our master theorem. The 3 cases are dependent on the ratio a over b to the d. And here we're going to state that if this ratio is greater than 1, less than 1, or exactly 1, we can exactly come up with the 3 cases defined by master theorem right over here. So let's quickly prove that. First thing first, let's say that what happens when my ratio a over b to the d is less than 1. So when this ratio is less than 1, you're going to very quickly notice that my series is decreasing. At the very first level, level 0, my work done is going to be O of n to the d. So level 0, I have O of n to the d. And then every level after that, 1, 2, to log b of n, I'm going to be doing less and less work. And so we can very easily say that the most work being done, again, like the most impactful work will be done in the very first level. And we can say over here that when a over b to the d is less than 1, the most amount of work done, or the work done in this, is O of n to the d. Similarly, what happens when a over b to the d is greater than 1? Well, going back to this analogy, we know that at level 0, it's O of n to the d. But then for every single future level, we know that our series is increasing, right? Because this term, a over b to the d, is getting larger and larger. And so this series increases, and our sum, this geometric sum, the sum is given by its last term, O of n log b to the a. So how do you derive that? We would say that at the very last level, we're dealing with n to the d times a over b to the d. And what is our last level k? Our last level k is log b n. So we're just taking this and raising it to log b of n. And so in this case, we can simplify this. And again, this is all in the textbook. I'm going to go ahead and just take n to the d as our common denominator. And we have a to the log b of n. You're just expanding the exponent. And then this becomes b to the log b of n times d. And again, this simplifies even more. And you would get b and b cancel. And you're left with n to the d down over here. This goes n to the d, n to the d, and n to the d cancel. And you're left with a log b of n. And then this, again, based on what we saw right over here with the width, when we had a log b to the n, this simplified to n log b of a. And so we can go ahead and just literally state over here, this is equal to n log b of a, and that is our final answer. So we're saying here that when the ratio a over b to the d is greater than 1, then the work done in this situation is n log b of a, with this very simple proof. And again, this is all dependent on the geometric sum being O of n to the d times a over b to the d to the k, so this over here. And we're essentially saying that's either the first or the last, or in the case when the ratio is exactly 1, it's all of the terms. And so in the last case, when a over b to the d is equal to 1, we can state that every single level we have O of n to the d work. Why? Because our multiplication now becomes O of n to the d times 1 to the k. And so this becomes, at every single level, we're doing O of n to the d work. And how many levels are there? There are log k times, log n, right? Because we're doing log b of n, but b is just a constant. So log n levels times O of n to the d work. So times O of n to the d work. And this will go ahead and give us the final answer. So we essentially just proved master theorem with these three cases by comparing the ratio of a over b to the d. And so I'm sure you're wondering, well, here we're comparing this ratio, but in master theorem we had, this type of d greater than log b of a. What's going on there? Essentially that ratio and this kind of comparison of d greater than log b of a is the exact same thing. If you write it out and you take the log of both sides, you'll get the exact same ratio. But that is the proof of master theorem in a nutshell, by taking our branching factor, expanding it out, and going through the three cases of comparing the work done at every level based on the ratio of a over b to the d. So again, if it's less than 1, you're doing O of n to the d work, you're taking the first term. If it's greater than 1, you're going to take the last term, or essentially the last level of work, which is again our kth level, or like the maximum level is log b to the n. And then last but not least, if the ratio is equal to 1, then in this case, all of your terms are equal and you have log n terms. And so the final answer here should be log n times O of n to the d, which is just equal to O of n to the d times log n. Fantastic. All right, so in this final section of the video, let's go ahead and discuss a very simple algorithm, the peak element problem. Come up with an algorithm, prove the correctness, and the runtime of this problem. So let's dive right in. The problem here is stating that given an array of integers, find a peak element. And so a peak element here is defined as any number in this array that is not smaller than its neighbors. So if I was going through this array, I would immediately notice that 7 is a peak element. Why? Because here 7 is greater than 4 and 7 is greater than 2. And so any number in my array that is greater than its other neighbors would be considered a peak element. And the goal here is to just find 1. So give me back 1 peak element. So you could easily argue that 12 here would also be a peak element, and that would be a completely correct answer. To cover a couple ground rules of this problem, if this array was in increasing order, then the very last element, the corner element, would be a peak element. If the array was in decreasing order, then the very first element would be a peak element. And then last but not least, if all of my numbers are the same, so all 2 or all 5, then any number or every element here is a peak element. So with that said, feel free to pause this video and take a stab at this problem. Come up with an algorithm that will probably use divide and conquer. come up with a proof of correctness, and then a runtime using master theorem. Go ahead and pause this, and then I'll dive right in a couple seconds. Awesome. So right off the bat, the simplest solution here is traversing through this array. And so you can kind of go from the first index to the last index, and in a very brute force approach, check every element to see, okay, is this a peak? Is this a peak? Is this a peak? Until the very end. And so that would be one way of solving this. You would say that, okay, start at index 0, and then et cetera, up to index n-1, check every element and see, okay, is this a peak? Is this a peak? And the runtime of this would be what? O of n. Is this efficient? No, not really, but this definitely works. Now, the second approach would be the divide and conquer approach. So the divide and conquer approach here would look something like this. So my algorithm would work as follows. I would say that find the middle index of my array. So find the middle index. And once I've found the middle index, I'm going to go ahead and check to see, is this is this a peak? So is this a peak? Okay. If it is a peak, then I'm good to go. I can stop this algorithm and I'm done. If it's not a peak, then what I'm going to go ahead and do is check the left-hand side and the right-hand side of my peak. So imagine in this case, like the middle element, let's say is 8, right? I'm going to go ahead and say check the element 8. And then if 8 is not a peak element, that means that there is a number either left or right that is bigger than it. So you check the left element. If my left element is greater, then I can create a new array that is sectioned off to be 3 to 6 and find a peak inside of this element. And if my right element is bigger, for example 12, I would section off this array and find a peak element inside of that. So to write that out in words, I would say find the middle index. If this is a peak, fantastic, I found my peak. If it's not a peak, then what I'm going to go ahead and do is kind of check the left element. And if it's greater, I'm going to go ahead and do what? I'm going to go ahead and create or run this exact same algorithm, run algo on array of index 0 to this left element index. And so kind of like mid -1, if you want to go ahead and say mid being the middle index. And very kind of similarly, check the right index. So if that did not work, check the right element. And if that's greater, and if it's greater, I apologize for my handwriting, by the way, guys. Sorry about that. Then run the algo on the array index, which is mid +1 to the end. Okay? So very, very crude handwriting and very crude like explanation, but this would be my algorithm. And why does this work? Why can we say that, keep on doing this, subsect my array from like, my entire length to this half or this half consisting the left element or the right element, and keep on doing that until a peak is found? Well, because of the invariant. So we can say over here proof of correctness, we can say right off the bat there's an invariant. And our invariant is that there always exists a max value in my array, right? There's always a max, whether all my elements are the same or there's one element that's going to be, greater than the rest. And so here what we're essentially saying is, since there's a max value in my array, I'm always going to be working towards kind of like a hill or a peak. So imagine that I'm walking down this road. And so I'm starting at 8 and I'm walking down this road. If I had an option to go towards higher ground or lower ground, which one would you choose? The goal here is not to find the largest peak or the biggest peak, but just to find a peak in general. So if I'm starting at 8, my goal here is to find kind of like a larger ground or a bigger ground comparatively. And so I kind of check my surroundings. I see 6, I see 12, and I want to go to 12 because it's the larger ground. And so I'd head over to 12, and I do the exact same thing. I would be like, okay, let me look at my surroundings, and my surroundings here I'd be between 9 and 5, so probably 9. And I would say, okay, am I at a peak yet? No. But I do see for a fact that 12 seems to be larger of the two. And so I go from, I'm at this array, like this subsection of an array. I'm at my 0.9, and then I would recreate this kind of mini array of 12 and be like, oh, I found my value. And so essentially, the proof of correctness here would be you state this environment, true, there always exists a max value in my array. And then we can essentially say that at every at every recursive step, we choose to move in the direction. We choose to move in the direction of a larger value. And we essentially guarantee that the new array that we run our algorithm on, our algo on, has a peak, right? Because if we're moving in the direction of a larger element, there will be a max value in my array that we can select as a peak. And so essentially, again, this is a very crude proof of correctness, but all we're trying to say here is that at every recursive step, we are breaking our array down by half, and we're stating that in my new array, there will exist a max because I'm moving in a greater direction. And so as I kind of break this down further and further, either I get lucky and my middle element will be the max at some point in time, or I will move and decrease this array size slowly and slowly until it's just one element, and that one element will be my max value. So you could use some sort of like induction theory or step, but it's kind of like a crude proof of correctness that says that since you're moving in a max direction, we'll eventually find some local max or ultimate max of my array. Perfect. And now last but not least, I want to discuss the runtime of this algorithm. So the runtime of this algorithm, we can very efficiently use a recurrence relation and come up with the runtime. So what is the recurrence relation of this peak algorithm? Well, we can go ahead and say that T of n is equal to what? Our branching factor here is actually just 1. We only care about the left side or the right side. We're not expanding both at every single level. So we're going to say 1 times t of, and in this case, our kind of like division factor here, or the amount of work being done in every subproblem, is divided by 2. We have a subsize of 2 because we're dividing our array in half every single time. So we'd say t of n divided by 2 plus, and how much work is being done at every step? Well, all we're really doing is we're comparing to see, is my middle value greater than my left or my right? And so the work here is actually just O of 1. 2 simple comparison operations. So plus O of 1. So if I were to write out A, B, and D for master theorem, I would go ahead and see over here that A is equal to 1, B is equal to 2, and D is equal to 1. Or D is equal to 0. Because n to the D, to get 1, D has to be 0. So in this case, what happens to our actual relation between D and log B of A? So D is equal to 0. Log B of A is log 2 of 1, which is equal to, in this case, 0. And so we immediately notice that 0 is equal to 0, or D is equal to log B of A. And based on master theorem, we can go ahead and say over here that if D is equal to log B of A, then this is equal to big O of what? N to the D, n to the D times log n. And so in this case over here, D is equal to 0, so n to the 0 is just 1, and this is equal to O of log n, final answer. So that was a very quick run through of how you would attempt to kind of solve an algorithm with, coming up with the divide and conquer approach, a simple proof of correctness, and then the runtime using master theorem. Thanks so much.